Filters. So the concept of filters is broad, right? We have filters for our oil, filters for our air, filters for the images. Heck, even a lot of popular neural network architectures rely on filters. So this concept, takes something. It's a generally a pass. You let some things in, you let some things out, you condition things. It is typically a process of refinement and sorting. So how does this apply to images? Well, we're going to find out. But first, let's talk about flies. So consider we're tracking a fly. It's buzzing through the air. We have a camera looking at it. So every so often, several times a second, we'll take an image that has the fly in it. And we have, maybe a good algorithm. We know it can detect flies on top of the image. Perhaps we're doing this over a green screen because we're doing a research study. So we can easily find green background versus black grayish fly. There's some noise in the sensor, so it makes things a little difficult. Perhaps the fly is moving really fast, and when the wings go, they get blurred. So it's hard to maybe tell the edges of the fly. So our goal is to actually reconstruct the fly's path to learn more about how they move through the air. Problem is, we can't rely on any individual movements because there's a lot of noise going on, right? We don't know the edges of the fly. The actual exact location may be hard to infer. So what would you do in this situation? You as university students embarking upon a journey of adventure here, trying to figure out this scientific path, trying to make this experiment happen, trying to collect the data to talk about flies. What would you do here? How would you can't really improve the sensor. Maybe too expensive. Maybe that technology doesn't exist. But we have all this data. Any thoughts? Ooh, I like this though. I see a lot of chin scratching. That's a precursor to thought. I guess there's not enough beards in the classroom. Gotta stroke the beards. What do you think? We have all these images of slightly fuzzy flies. What would you do if you were trying to, find out the effect of gravity on an object? What would you do? Yeah.
Well, for this,
Yeah.
would it be that you would try and take a photo without the fly and see what it looks like without that, and then try and remove that noise?
Yeah, could possibly work. Yeah, you try to remove the noise. Now that would rely on sensors, apparatus, setup, things that we don't know. Effectively, what we're trying to do here is denoise the image, but by using several images. Just like if you would drop something off a table and record how long it takes to hit the ground, you wouldn't do that just once and record, right? What would you do? What would you do to get a reliable measurement? Oh yes, please. Sorry, I didn't see your hand. Exactly. You would record it multiple times and see the average. You'd see mean, median, average, standard deviation. You get all this information about sort of the qualities around your measurement process. And so this is what we'd do here with the fly. So what we do is we'd take a few samples to give us a better picture. This way, the noise sort of cancels out over the average. Any one image can be wrong in certain ways, but if you have multiple images going on, you'll get a variety of error and a variety of truth, and averages help us out here quite a bit. So here we can, so if we're taking these image sequences over time, and one of them is off by a few millimeters in introduction, millimeters really matter for us. It's less likely that millimeter offness will compound from image to image to image. So we'll sort of get the boundaries of our error because we have more information, more experience now with the problem, right? So instead of using a single example, let's use a weighted average of a couple samples, before and after. So we want to see like where is fly at time 1? Well, perhaps we want to look at time 2 and 3 and time 0 and -1. Right? That way we can take a look to see where has the fly been, how fast is it moving, sort of like we did, sort of like some like a implicit estimate of velocity in motion. And combining all those together, we'll see, perhaps, if the fly was flying at some sort of relatively steady speed, the distance between time 1 and time 3 would be, like this much. Then you could start chopping off the edges, right? And then so through averaging, you would see perhaps the location of the fly being pretty close to t equals 0, law or the position in time 1. So you'd sort of correct for or use the averages to denoise. Right? So there's a lot of power we have when we're using more information, surrounding information, adjacent information, perhaps even correlative or causal information to find out the answers to our problems. So this is sort of like what this filter process looks like. So we want to find the position of fly at time t plus 1. So we have 1, -1, -2, 2, 3, etc. So what we're doing is we're bringing all that information together and using a filter. Or in this case, we're simply doing a sum, or a sum divided by samples, or an average. Right? And so you can do this, and you can move this across you can use this in a window form. So here we're using 5 consecutive images, 5 consecutive measurements to get a weighted sample for 1. So we're bringing a lot of information together. And you can do that across the board, right? And now you can reconstruct some weighted estimate of the fly's position at t plus 1, t plus 2, t plus 3, with something that has much more accuracy than using a single image. So instead of having, developing a new sensor in order to get better information, or developing a new green screen technique, or having to do something really expensive, here we can use the power of averages and computation to take the same hardware we had, the same sensors, the same camera apparatus, the same background, the same room, and get more precise information from it. So these filters are interesting. We'll use filters in this case. What we want all of the weights of a filter to add to 1, because these weights define how a filter works. This is a little abstract right now, but we're going to cash this out with a lot of examples. But the basic idea here is that we want some input, and we run it through a filter, and we get some output that we'd like. And this filter does work for us. So we have had a look at filters, right? We have our built-in filters that we ran in class, right? Where we had threshold filter, our gray filter, our inverted filter, blur, erode, dilate. All of these are using the same type of process that we did to get information about the fly. We're using adjacent, coherent, sort of like neighboring information to do something neat, to do something we couldn't have done before. Oops, there we go. And you can reapply filters. So we could apply blur, and then we could apply inverted filter. You can apply them consecutively and alter the image even more each time. We call this iterative filtering. The weighted mover average filter multiple times. If you use these a bunch of times, you'll get a Gaussian probability distribution out of it. So there'll be a little bit, so I know some of you have taken a lot of math, but I imagine some of you are intimidated by math. I think I was really intimidated by math my first and second year. So we're going to mention some math things, just to connect to specific people who want to push us a little further. But please don't be too intimidated when I say things like Gaussian probability distributions. Now, the number of samples you need, like the number of different frames we needed to find the fly location, is referred to as the filter support. That's like supporting information, supporting samples. Yeah, support. Definitely not like Sona or something from like League. Different type of support. Generally, we want the support to be local or something that has some relative like adjacency, some coherence to our filter. And we want it to react to local variation, and we want it to be easy to compute. So let's take a look here. I think I'll actually come back to this slide. I don't like exactly how I've structured this. Okay. This is a filter. So what we're doing here is we're replacing a pixel by a weighted sum of the pixels around it. So here you see this. We have a 9 surrounded by a bunch of -1s. This is the sharpen filter. When you sharpen images, this is exactly how it works. So what you're doing is you're taking a pixel, and then you're giving it, that pixel itself, a weight of 9, and then you're weighting in all of the colors of the surrounding pixels. These 6 around it, top left, top right, bottom left, and left. Adjacent pixels. And we're taking those as value -1. And so if we take all those color values by -1, and then we multiply the color value of the pixel in the middle by 9, and we add all that together, that's our filter. But also notice that this adds up to 1. So there are 8. I'm sorry, I said 6 earlier. There are 8 adjacent boxes and 1 center box. That equals 9. And notice here, we have a 9 in the middle and 8 -1s. So that ends up being 1. So our filter has this property satisfied. That means it's sort of like keeping some sort of proportionality with the color information. And so you want to do this for every pixel. And so what this ends up looking like is something like this, right? We have on the left here a big grid of pixels. Notice that when you do filters, you tend to have a padding of zeros around it, a padding layer. But what we do here is when we want to find the filter value, when we apply on this, we want to take this as our original information in the back, and we want to apply this 3x3 filter to it. And then we want to take that filter result and plunk it in the same location in sort of like a new like image storage space from the other, so we don't destroy the original image information. Right? And so we go through here. This filter is an interesting one. It's 4, a bunch of zeros, and -4. So this one actually doesn't preserve weighting functionality. This middle should be a 1. There are lots of different filters. Image filters, you want there to be 1 at the end. Other filters in the world may not be quite as exacting. But what we do is we apply this filter, reduce those 9 bits of bits of pixel information down to 1 pixel information. And this is a different view of this, right? So here we have this padding around our image. We have all this image data here, and we want to filter this too. And so this gray area is the region of filtering. And this is our filter. And then we'd apply that filter. We'd multiply the 0 times the 9, and the 1 times the 5, and the 0 times the 0, the 0 times the 1, the -4 times 2, etc. And then once we get all of those multiplications in, we sum all of those answers together and put that in our result. So this is actually taken from convolutions in machine learning. Have you ever heard of a convolutional neural network, SCNN? These are pretty popular in image generation and machine learning tasks, deep learning tasks for quite a while. Because what's happening is these little filters, what they do is they abstract information. So you learn a little bit more. You make a relationship with the things around you, and then you use it in the statistical learning process. So typically filters in machine learning, which is where you find so many of these examples now, they add up. Typically the filter sum 0. But in images, we want them sum 1. Okay. Let's do a little bit of animated view here. So we want to filter this pixel. So what we do is we apply. This is our filter region. It's a 3x3 filter. And we apply our sharpen filter over it. And then we do the math. We take -1 by whatever was in this before, -1 by whatever in this cell before, -1, -1, -1, -1, -1, and 9. Do all those multiplications, sum all the results together, and plunk that value in the appropriate location in our results output image. Then we slide the window over by 1, and we do it again. Slide it over, do it again. Right. So does this sort of like make sense? Like the basics of how this filter process works? It's math that you've learned in 4th grade applied to problems that you're learning in university. Okay. So I'm going to go back a little bit now that we've seen how this works. I want to go back and talk about convolutions. So convolutions are sort of what we call this filter process applied to 2D images. Right? And so we rely on using the pixel's neighbors to affect the pixel itself. So for those of you who have perhaps taken some calculus, convolutions can be thought of as the integral of the effect of one function, f, the filter, on a second function, g, or the image. Right? And so this process of integrating information through this sort of like calculus-like conceptualization of what filters and images are provide this power. So in discrete representations, does anyone know what discrete is in this case? Have you taken any discrete math classes? Okay, maybe math hasn't been super popular with this particular group. That's fine. So all that it means is we're not working with like an open continuous space. We're making it into chunks. We're quantizing it. In this case, our quantized space is a grid of pixels. It's kind of nice. We have our own little individual buckets to work with, and we don't have to work with like the infinite variety and variation of something analog. Right? And so here, what we're doing is we're doing a summation. So we're approximating an integration with summing a bunch of small values, some quantized values. Just like when you learned limits in calculus. The limit does not exist. And so we look at the example. So I kind of like wanted to go to the example first and then sort of like bring this information back in. Right? So once again, the intuition here is for every pixel, we'll an average of its neighbors. The mean of average can vary. This is a weighted average. So we're averaging a bunch of -1 weights with a 9 weight for sharpening. And we apply it to a 2D image, right? And so once again, here's the code for it. Basically, for pixel ij, we want to get the pixels to the top left, the pixel to the left, the pixel to the bottom left, the pixel to the bottom, the pixel itself, the pixel to the right, I'm sorry, the pixel above, the pixel to the bottom. Oh, I messed that up a little bit. Anyway, there's one here for each pixel around. Reading this on the fly on my tiny screen isn't exactly helping me. I wish I had a nice bright display like this. Do it for every pixel. Window, result, slide it over, apply the filter, input the result, slide it over, apply the convolution, put the result, and you'll slide it over until you do the entire image. So what does it actually do? So this is our sharpen filter here. Oh, I actually messed this up. This should go first. So the left area is an intensity of 200. So it's just a brighter gray, right? If you put in color 200, this is what you'd get. On the right side, we're dealing with an intensity or a grayscale value of 100, right? A darker gray. And we want to apply our filter here, our sharpening mask. So there's a bunch of pixels on here, but there are two major cases we have to think about, right? What if the filter is applied with an area that's wholly within this intensity 200 zone? Then what if it's only in the darker zone? Our other two cases is what if 1 pixel is in gray and 2 pixels, or 1 pixel is in the lighter gray and 2 pixels are in the darker gray? Or what if it is 1 pixel in the darker gray and 2 in the lighter gray? Those are all our different sort of like result cases from this image. Let's see what happens. So here we have that top left case. So since all of these are 100, we apply our -1 times 100 for the top left, top right, etc. All the adjacent pixels, the 8 adjacency pixels. And then the pixel itself is the value 100 times 9, or 900. You add all this together, and you get the original value back of 100, right? No big shock here. Basically, we have the exact same value. So we're going to have, like -8x plus 9x, which would give us, 1x, right? Give us x back out. So great, awesome. That means if there's nothing to sharpen, we're not sharpening anything, right? There's no edge there, no difference to filter. And that applies also to the darker gray at 200. We have all these. We have 8 200, negative 200s being 1600. And then we have 9 times 200 in the middle, which is 1800. 1800 minus 1600 is 200. We got our x value back. Now let's look at the other cases. What does sharpening even do then, right? Why are we even doing the sharpening thing if we're just getting the same values back? Well, sharpening really matters when two edges come together, when there is a space where we have information or context to show the distinction, to sharpen the distinction between two color regions. So if we're right here, if we're 2 pixels into the lighter gray area and 1 pixel into the darker gray area, we have to fill in the appropriate values. So now all of these had base pixel values of 100. So -100, -100, -100 in all these areas, 100 times 9 in this area, and then -200 in the 3 right areas. So let's see, it'll be -600 plus -500, so it's -1100 plus 900. So that ends up being -200 as the value. Right? Well, that has given us this sharp, low intensity border. Right? So if your color value ranges between 0 and 255, and all of a sudden you're getting a -200 in P5, we take values that go less than 0. We make them 0 when color function interprets them. Sort of like clamps it or sets the lower range to 0. If it goes above 255, it brings it back down to 255, clamps it into 255, all into that range. And so this gives us a value of 0, right? So now we have a dark edge, a 0 edge, a 0 weight edge. So it's black all along this left-hand margin, left-hand border. Similarly, we have applying the same filter where we have just the left 3 pixels in that region being the 100 intensity value and the other 6 being 200, right? We do our math again. -100 for all the left areas, -200 for all the surrounding darker gray areas, and then 1800 in the middle, right? So -300 plus -1000, so -1300. So 1800 minus -1300 gives us 500. Well, what does that do? Well, using the same logic we applied before, if it's over 255, it brings it back down to 255. So now we're going to have this very dark region of 0 right next to this very light region of white. And then all the other colors are the same. So what this does, this little filter, it gives us a really stark, highlighted edge, sharpens the distinction between two regions. All right, does this make sense? Did I just like lose everyone? Luckily, this is, I think, fairly straightforward math, but applied in like, I think a fairly like interesting way. The intuition of a sharpening filter, every time you use that sharpening tool in Photoshop, this is what it's doing. There's no big mystery here. We got a bunch of numbers. We're doing some numbery things and get some more numbers out. All right. Let's unsharpen. Also known as blur. Blur filter, blur motion effects that you apply post-processing to frames of video or into video games. They all use this similar technique at their heart. And all that it is applying this filter. We weight everything by a 1/9. There are 9 boxes that summed up to 1. So the filters can be any size, right? So we'll take a look at that in a moment. But as long as they add up to 1, you have a filter. Now, some filters do more coherent things, some filters do less coherent things. This filter takes all of the pixel values surrounding a pixel, including the pixel itself, and averages the colors together, like mushes it. Like if you had, like when you put a bunch of paint together and it makes brown, this can be kind of what blurring looks like. It destroys the distinction between the color areas instead of sharpening them. It avoids sharp changes in intensity, whereas sharpening makes the sharp changes even more sharp. Okay, let's apply our blur filter. All right. Maybe I should wait until someone figures out the math for me so I can be lazy. I don't think I'll do that, but we'll move on. Oh, well, maybe I'll have to, okay, because my blur slides didn't seem to have saved. Okay, we can recreate it, though. Oh, that's a real bummer. I spent a long time on this right before class, too. Is it just out of the way? One moment. Let me see if I accidentally hid the slide. Fine. Okay. We'll do a little slide surgery on the fly here. So we won't need this one anymore. We're not doing this filter. We're doing this filter instead. Okay. So we want to apply the 1/9 filter. So what's 1/9 of 100? 11 point with a bunch of ones behind it, right? So we'll just do 11.1 and we'll know that it repeats ad nauseum, ad infinitum. So same here, all these are 11.1. Whoops. Okay, so what does this add up to? 100, right? We took something by a 9th and then multiplied it by 9, right? So great. Look, we got our 100 back. Okay. What's 200 divided by 9? This should be a real... Huh? 200 divided by 9.
22.2 repeating.
Exactly, 22.2 repeating. $222, no. We don't want to break our symmetry here. And what does that equal? 200. Exactly, right? All right, so now we're getting a little more interesting. Now we're going to do a little more math. So we're filling in our 1/9 values. now we're going to have to add some stuff up. I'm actually going to pull up my calculator for this. And maybe I can pull up my calculator's history. Oh, right. So 2 22.2 repeatings and 6 66.6 repeatings gives us this value. With 33.3. That didn't work as planned. All right, so I mean, what did that do now? Now that we're on this border where we have two intensity 100s and then one row of intensity 200s, and we get this value of 133.3 back, repeating. What does that mean? What did we just do? What was the effect of this? Yeah.
You created an in-between value so the shade's different.
Right, exactly. We brought some of that darker value into that lighter value area, essentially, right? And so we found an intermediary color. Now if we do the same for this, and now you've got to see me type a bunch of numbers. What do you think the result is? You can use proportions to figure this out. What would be another in-between value? Please.
166.6.
166.6 repeating, right? So now, thank you. Now we have this nice area of transition from the light areas to the dark areas using the filters. It smooths out that sharp, stark contrast between intensity 100 and intensity 200. And so would have an intensity 100, and then instead of having the stark border, we'd have sort of like 2 pixels over from the border, we'd have 100. Then right next to the border, we'd have 133. Then just over the border, we'd have 166. And then finally back to 200. So we sort of like stretched out that color value. Any questions about this? Think you can recreate this? Think you can recreate the math? Like, let's say I gave you a pixel grid on the final exam, and then I gave you a 3x3 filter. Do you think you could fill out like 3 or 4 areas of pixels in that filter? The answer should be yes, you can, because it's very likely to be on the final. Not going to pull any punches here. This one's a fun one. So that's blur. Right? So what if you want your image to be even more blurred? I accidentally gave you the answer. What would you do? Yes. You could run it through the filter again. But would that actually start blurring things? You've already got your averages around. What if you wanted to keep your original image around still? Yeah, you can make the fractions smaller, but if you have to preserve one, what does that mean you have to do? Make the filter bigger, right? So, if you had a 4x4 filter, you could divide everything by, by the number of pixels in the filter. So it wouldn't be 4x4. We'd need 5x5 because we have to have the center pixel. So 1 divided by 25 for each one of the pixels. And then you could expand it out and expand it out and expand it out. Right? As long as you have each pixel being 1 over the number of pixels in the filter, you'll preserve that one property. that sum up to one property. And so the bigger you go out, the more you're including into that large average. So if we had a bigger filter, instead of having like 2 gradient spaces, instead of having like 100, 133, 166, 200, you could have way over here, it'd be like 10, 110, 120, 130, 140, 150, 160, 170, 180, 190, 200. And so you'd have that whole thing smeared out, like you took like 2 blobs of paint and just like Bob Rossed it in an arc, in a line. But you can apply it repeatedly as well. Thank you for the suggestion. So these convolution examples, there is a bug in Open Processing's canvas that isn't giving me the correct pixel information. So I'll get you some examples of the convolution soon. But I do have some working examples in P5JS's editor. Instead of in Open Processing, there's another editor on p5js.org, or editor.p5.js, or p5js.org, that we've looked at a little bit in the past. So some of the ones we want to look at are edge detection, let's actually look at the example over here. Hi, Yogi. Oh, right. So here, we have a convolution filter. Is this text visible for those in the back? Excellent. Thank you, thank you, thank you. So what we have here are first defining our filters as 2D arrays, right? Hey, look at this, our sharpen filter, our buddy, with the 9s surrounded by -1s. And now we have our small blur filter, our 3x3 blur filter that we did the example together. A bunch of 1/9s. Then we have a medium blur filter of a bunch of 1/25s. Then a large blur filter. Where's the border? There it is. With a bunch of 1/49s. Right? You can make these filters as big as you want, but the bigger you make the filters, the longer it takes. So now we have 49 things to add together, to compute and add together, as opposed to 9. And every time you expand it by 1, it grows exponentially. By the power of 2. Big O n squared. So we're preloading our image. This one's a spacewalk image. We're setting our canvas to be the exact size of the image. We're doing funny business. And we're loading that image as pixels. We're getting some pixel density information just for fun. We're setting our background to be the image. And so what we're doing here is we are making sure that we have this W by W image filter area. So basically we're going to filter an 80 pixel by 80 pixel square. And the rest of the image will not be filtered. So we can slide around our little filter window. Okay, awesome. We're making sure we're using a sharpen filter and we want to get its size. And so we're setting load pixels. So we want to make sure that the pixels in the background image are available for us to use in the pixels array, just like we talked about in the last class. And so we're going through this pixel window, this 80 by 80 pixel window. And what we're doing is we're getting the location in our pixel value. So you all should remember this. It should look familiar to you. We're getting the X location and the Y location times the width of the image to get the number, the offset into that large pixel array where the pixel we want lives. And we're multiplying it by 4 because each pixel in that array holds an R, B, G, and A value for each pixel. So the first 4 values in the pixel array are the RBGA values of the first pixel in the top left. So we got to figure out when we want arbitrary pixel XY, where are we in that array? And so what we're doing here is we're getting that location. And then we're setting call our red C, blue. Okay. So we called our convolution function here. I skipped over an important step. So basically we're calling the convolution and we're getting values back out of it. We'll take a look at that in a moment, but we're getting a color data structure out, right, that holds an RBG and an A. And we want to make sure that we're placing the red portion of that color, the green portion of the color, blue portion, and alpha version of that color into the appropriate area in the pixels array. Right, so this should look familiar to you. Now let's look at this convolution function. The thing is actually making our filters work. So here we are. That could be some intimidating code, right? At this point, you should be looking at this and being like, wow, that's probably a lot. But all that it's doing is that exact same thing we did together. That math that we did, multiplying things, dividing things, or multiplying things by -1 and 9, or multiplying things by 1/9, and then taking the big square of that, adding them together, returning those values. That's all this is doing. It's code that pulls off that filter, that convolution, over the image region. So here we want to sum up. So the R total, G total, and B total, those are the red, green, and blue values for each one of those average pixel areas. So instead of working with one value per region, we're in not grayscale, right? We're in full color, we're in RBG color. So we need to sort of like, if we want to take 1/9 of all the pixels and add them together, well, we want to make sure that we treat the red channel 1/9 separately from the blue channels 1/9 separately from the green channels 1/9. So that's what these variables are for. Now we're going through, we're getting an offset here. So what we're doing, our zeros here is the top left of where we're filtering. And then the max size is how far to the right and down that little filter region goes, our little filter square. And so we're deciding, okay, what location are we looking at right now in the pixel grid? We're making sure that that the values don't go over the edge of the image. If you try to access something that's not in your array, sometimes that can be big trouble. May error out. And so what we're doing here is for our totals, we're adding to it the value, the value of the red pixel at that location, the red value of the pixel at that location, times our matrix value, 1/9, -1, 9. And we're bringing that in to the R total. And we're doing the same thing for green and blue. So this is where we're taking our multiplications and then adding all of them together. We're just doing it one time. So each time through this loop is going one of those cells. So we're going top left, top right, or top left, top right, then middle left, middle right, then, I'm sorry, I'm transposed from you, and then bottom left, bottom middle, bottom right. That's all this for loop is doing for us. We're adding them together. We're constraining it so it doesn't go below 0 or above 255. We're building a little color object, and we're sending it back. And that's where we get the C from, that we then update our pixel values with. All right, so luckily we're recording this, and you can go through this explanation again. I'm not going to ask you to like write a convolution filter, but this I'm using as a way of like pushing your code brains forward just a little bit. You've been exposed to something more complex than you've been exposed to before. That's how you grow. Put you in an uncomfortable space. Okay, let's run this thing. So you should note that we have it configured to run the sharpen filter right now. Let's scooch the window back over. So here's our rectangle. See how it's making all the color regions lighter and then darker? And then the black region, you can tell there's no effect at all. That's just like when we were in the fully gray region. Right? And so we're just sliding around this window with mouse position, our 80 by 80 filter window with the mouse position. All right, does this sort of make sense? We've built up enough of a case that you can sort of vaguely interpret what's going on. The regions with starker contrast are more interesting to look at. It also helps you see things that are barely there before. pops contrast that it's harder to see with the eye. Let's take a look at blur. Okay, so we'll change sharpen here to blur small. A little harder to see, but now you can see the details sort of like being destroyed. It's like taking one of those like little transparency privacy translucent screens and just like sliding it over the image. But, you know, this filter, it's not a very strong blur. It's just a small blur, a tiny blur. So let's look at blur medium. All right, now we're getting some more meaningful blur. Now you can see that sort of like blurring of information. It's happening much more strongly. And it's also slower. The frame rate doesn't look as high because we're doing more processing per pixel. So now we're doing this 25 times per pixel for 80 pixels. And we're doing it per color. So we're doing 4 times 80 times 25 math operations to make this filter go. And then we're adding all that together. And now we'll see what the big one does. Blur large. Not larger, just large. All right, now you're seeing a much stronger blur, right? And we did all this with our own code, with our own math. Nothing special to it. We just learned a trick. And now we can apply it with math. Okay. This one, fortunately, okay, here we go. So now, let's look at a different example. So this example is a flashlight. So it works similar to a filter, although in a larger space. So what we're doing here is we're taking the position of the mouse and we are adding in color information. The center of the mouse gives all the color information, and then a radius around it, it slowly gets less and less color information coming from the original image up through the darkness. So running this, see that we can see a little bit of the ship in the water, this flashlight. And what we're doing is using a filter like circle or a weight fall off, a lighting fall off, so that the center of the light is very bright and the edges show a little bit of the image, and then past the radius of the circle, it's black. Like this is like Where's Waldo challenge mode. Can you find what you're looking for, but you can only see a tiny bit of it at a time? Okay. Good, we will have some time left. So edge detection. This is a common image operation. And what we're doing is we're looking at large differences between values of adjacent pixels. Right? And so we want to see where the edges are. So it's kind of like applying a version of a sharpening filter on an entire image. Right? So changes in intensity are kind of the same as changes in color values. So we're looking to make areas where there's a lot of change in color from one pixel to the next pop up. Right? And so we can do this. All right, so every pixel, we want to find the location that we want to work with. Let's just have a ×4 by it. And what we're doing here is we're finding the left version of where we want the where we want to look at for the color information. So the 1 pixel to the left, and we're taking it times the image width. So we're looking for a difference between color intensity from 1 pixel and the pixel to its left. And then we're taking the absolute value of the brightness of the pixel. And the brightness function simply like returns like the average of the RGB values. So kind of like getting the grayscale version from it. And then we're subtracting one of those from the other. And we want to make sure that we're getting the difference. So if this one was smaller than this one, if it returns a negative number, we want to get rid of the negative value. We just want to see the distance between the two. And when we do that, we want to add that difference in color to be the color at the pixel's location. All right, so let's take a look at what this looks like. Is this actually what I'm looking for? Yep, there it is. So it took a while to run. But do you see the difference between these two images? Every time there's a shift in color, we make that shift more pronounced all across the board. And so edge detection, essentially, as you can probably tell from the side, is a full image application of the sharpen filter. So here's the kernel or convolution kernel that's used. Right, looks familiar. Well, if you apply that to the whole image, you get edge detection. But we have a bit of code here. Where do you think it fails? What is this not doing? What edges would this not find? Well, we have x minus 1 here. So we're doing x-axis images. What aren't we doing? Oh, your hand's up. No? Okay, just kidding. I wouldn't do that to you. We're not doing up and down. So we only get left and right edges and not up and down edges. Not horizontal edges, not vertical edges. But the code I gave you, and the example we showed does. And I'll give that out to you in class. We'll detect horizontal edges. All of our built-in filters: threshold, gray, invert, posterize, blur, opaque, erode, dilate. You can look at if you go in the documentation for, I believe, P5JS, or I believe it's there. It was in the Java in processing. It'll give you all of the kernels for each one of these filters. And so you can play with all of them in our built-in filters example. We won't go through it again. We don't need to see it like a third time in class. Anti-aliasing. Have a great day. Anti-aliasing. Who knows what that is? We talked about this before in class a little bit. Yes.
It's like it makes the pixelation more smooth. It sharpens it so where it's less noticeable.
It actually does the opposite of sharpening.
Oh, okay.
It takes something that looks like jaggies and makes it look smooth. And because we're working with like discrete pixels, and that's where the jaggies come from, the jagged edges, what it's doing is it's taking the pixels and sort of like blending their colors together to make it look smooth, but also destroys the edge information a little bit, right? And so we have this built into processing. If you start working at a lower resolution than you like, and things start getting a little, you can start seeing the edges where things are drawn, you can use smooth. This also works on bringing bitmaps that you then like blow up and use at various sizes. You can call the smooth function, and it will do this blur operation strategically called anti-aliasing on the edges of your image and make them look smooth. Now, that's the last slide, but there's the mouse. Get out of here. We have our example here, right, of our animated sprites, our leaf example, right? And you see a lot of jagged edges here, right? Like the cape, the cloak. There's a lot of blocky pixel-looking areas. So notice at line 16 here, I've called no smooth. So the thing about working in a web environment is it does anti-aliasing by default. So if I just leave it by default and leave the default smooth operation going, it kind of looks bad, right? So we have anti-aliasing. It looks less blocky, but what it's doing is it's applying a blur operator over our good pixel art, right? We don't need that. So this is if you are planning on making a game with sprite animation for your final project, please do me a favor. I'll be very happy if you turn on no smooth or if you disable smoothing and get us back to this. All right, so this is where I wanted to end the lecture portion today. We have 15 minutes left to talk about groups, talk about projects. I'm happy to take some Q&A at the beginning here. I want to give you some time to make your groups, talk about your projects, ask questions about proposal. All right. See you all in the recording.